This is number 68 in chapter 15. It asks us to calculate the Ka for a weak acid, but it's a general acid, so they're just telling us it's HA, not very specific. Question goes further to say that we have a 0.115 molar solution of HA, and that we also have a pH equal to 3.29. And we want to solve for the Ka. So since it's a weak acid, we need to have an equilibrium representation. And from that we can get at an equilibrium equation, which is equal to our Ka for this general weak acid. And that's ultimately what we want to solve. So we have to construct an ice table. And we know our initial concentration of HA that was given to us is 0.115. We are not beginning with any of our products. That tells us where the positive change is going to go. It's going to go towards our products. And now we have, at this point, if we solve for our equilibrium, right, we would have two unknowns. We wouldn't know what X is, and then we also don't know what Ka is. But remember, every time they give us a pH, that pH is really telling us H3O plus concentration. So remember, 10 to the negative pH is going to equal H3O plus. And so 10 to the negative 3.29 is equal to 5.128 times 10 to the negative fourth molar. And remember, that's H3O plus concentration. So that's our concentration right here. And also right here. Because those guys are equal. Those are both X. So those are both the 5.128 times 10 to the negative fourth. And then we need to have this 0.115 minus X. I kind of ran out of room there, but that's where that 5.128 should go, is where X is. And so I'll write that over here. Right, our Ka would be equal to 5.128 times 10 to the negative fourth for both our starting materials. And then you'd have 0.115 minus 5.128 times 10 to the negative fourth for your HA. And when you solve for that, you get a Ka equal to 2.297 times 10 to the negative 6. Again, the trick here is, again, remembering always that pH ultimately leads you to H3O plus. And so that's an important feature to always remember. That is number 68, chapter 15.